Any professional knows.
Okay, so today we're going to learn about something that is fairly difficult to explain, and I think pretty hard to understand. And so it's going to require you to pay pretty close attention to the things I'm saying, ask me questions, that kind of thing. I find myself, when I'm planning for this lesson, I find myself spending half of my time looking for a reason not to do it at all. The other half looking for a movie that does it for me, and there's nothing. I have to do it. And it's really hard. So I want to start. With a question that will be seemingly irrelevant. And the question is, if I take a planet in the middle of the universe, and I say that that's the only planet in the universe, it's the only mass that exists, does it have gravity, even if there's nothing for it to exert its gravitational force on?
No.
I mean, it's a planet, so therefore
Because
there's
there's no equal
Yeah.
and opposite.
something for it to exert its gravity on.
Doesn't everything with mass have some sort of gravitational pull?
True. But can it have a gravitational pull without something to pull?
But it has the, is there even on the planet?
Nope. Yeah, there's a couple of
It can pull
Like the
things
pull
on the
exists and
planet.
it's just
The
waiting for
planet
something
can
to
pull itself.
Right?
No.
Yes, that's a really good way to
What
put
was
it.
that?
Can you repeat what you say?
The pulls exist and it's just waiting for something to pull.
Okay, so it has an existing pull. It's just waiting for something to pull towards it. Okay, that's a good way to think about it. Another way to think about it is that gravity influences the space around it. To the extent that many of you know, things that have mass bend the space around it. Okay, bending the space around it doesn't rely on something else to interact with. Objects that have mass themselves influence the space around them without requiring another object to interact with. The Earth has an acceleration due to gravity, even if there's not something actually accelerating at that moment due to gravity. It has intrinsically this property which allows it to accelerate things, which it allows it to exert a force, and it influences the space around it. When we learned about gravity, we learned that it was a non-contact force, right? So many of the forces that you have learned about so far, like normal force and tension and whatever, those are all contact forces. You experience contact forces every day. But gravity is what we call a field force. And there's a reason that we call it a field force. It's because it influences the space around it and creates what we call a gravitational field around it. The space where it can influence an object when placed in that field. If I place an object in the gravitational field of the Earth, it will experience a force. And that force will cause it to move this way, towards the Earth. If I place an object somewhere else in the gravitational field of the Earth, it will move towards the Earth. If I place an object somewhere else, it will move towards the Earth. Okay, and so having a field doesn't require interaction with another object. Having a force does. So when I emphasize that the force of gravity is not equal to the acceleration due to gravity, remember some of you used to write that all the time, and I said, no, it's mg, where m is that other thing required to make this g into a force. Okay, but this in itself is an intrinsic property of the planet, of the mass. And that's the field. Yes?
Is there a point where the field ends, and if you place an object there, it would not feel the gravitational pull?
Technically, no. So this is not something that I'm expecting you to know, but it's something that I think is really interesting. If you look at the gravitational force between two masses, call this M1 and M2, the gravitational force equation between any two masses is equal to some constant times m1 times m2 over r squared, the distance between them. This looks just like Coulomb's law, except it's dependent upon a different constant number and 2 masses instead of 2 charges. Okay, it still has the r squared in the bottom, just like Coulomb's law has r squared in the bottom. Coulomb's law, if you recall, is k q1 q2 over r squared. Charge, charge, constant, and then the distance between them squared. These are both what we call 1 over r squared laws. They both mean that the force drops off as a function of 1 over r squared. So what that means is if I want this number to equal 0, what does r have to be?
Some infinitely small decimal. Because it would be impossible to actually. It would have to be
Infinitely
0.
large number.
Oh,
If
yeah.
you have something in the denominator and you want to make the whole number go away, that number in the denominator has to be infinity. So technically, no. Technically, there is no place in space that this object does not have an influence upon. Okay. However, we say it drops off as 1 over r squared, which means if I double the distance between, if I'm on the surface of the Earth, I experience an acceleration that is 9.8. If I double the distance to the center of the Earth, so I increase this distance to here, then that drops off by a factor of 4, because it's 2r, but it's squared. Okay, so this becomes like 2.5 is my value of gravity up here. If I double that distance again, now it becomes, if I triple the distance here, it becomes 1/9 of that, so like 1. If I quadruple the distance, it becomes 1/16 of that, so like 0.8, something less than that. Okay, but it drops off and it gets really, really close to 0 really, really fast. Okay, so we consider it to be 0 at some point. But the point is that we have this force that requires 2 masses of interaction, but without a mass to interact, there is still a g value, there is still an acceleration value, and that is the gravitational field. Okay, in the gravitational field we represent with vectors. And it's, for gravity, there is no such thing as a repulsive gravity, right? It's always attractive. So if I were to put an object here and sketch in the direction that object would follow, it would be that way, right? It's going to go towards the Earth. Here, it's going to go that way. 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 It's always towards the Earth, right? There's never really a question about that. When we talk about charges, and we talk about electric force is also a field force because it does not require contact in order for there to be an interaction between 2 charges. They're not touching, but they're exerting a force, and that force can be calculated using Coulomb's law, k q1 q2 over r squared. But in the same way that a mass by itself can influence the space around it, a charge by itself can also influence the space around it. And it does not require another charge to be present in order for it to create a field around itself. Okay, the field is not something physical that you can see. You can't see the gravitational field of the Earth. You can't see the electric field of a charge. Okay, it's something that we represent in many different ways, visually, but it's not like a real physical thing that's actually there. So in the same way that I was like, okay, so we can imagine that you put an object in the Earth's gravitational field. We can imagine that we place another charge in this charge's field. And then we can pretend or imagine what will happen to that charge when it's placed in that field. Okay, so we've got this positive charge here, let's say, and it's creating basically an infinite field around it where it could interact with something. It doesn't have to be interacting with something. It could be, it doesn't matter. Okay, it's all about, it's intrinsic. It's a property of the object itself, not the interaction between 2 objects. Okay? And with charges, the difference between a charge and a gravitational field, well, there are lots of differences. 1, it's dependent upon charge and not mass. But 2, we can have attractive and repulsive forces when we talk about electric force. Gravity is always attractive, right? But electric force could be attractive or repulsive. So the direction of the field could be like in or out, right, depending on the situation. Now, when we are trying to determine the direction of the electric field or what is happening in the space around this charge, we have a convention. And what that means is everyone in the whole world uses the same scenario to imagine their electric fields. Because if I said I put a charge here and I say, which way does it go? Your question would be, what is this charge? Is it positive or is it negative? Right? And you can't just like make it up. Because then everyone in the world would have like opposite signs on their electric fields. So instead, we all imagine in the whole world that we placed a little positive charge in the field. Okay? It's what we call a test charge. It's a thought experiment. It's an imaginary thing. Okay, so and it's not always imaginary, but it can be, right? I say, in what direction is the electric field if I place an imaginary test charge right here? You would be able to tell me which way the field is. Which way does it go?
Away.
Away, yeah. I mean, you don't have to say like at an angle of, 172 degrees, but it's away from the positive charge. If I put a positive test charge here, it would go away. If I put a positive test charge here, it would go away. Okay, so the electric field goes away from positive charges. Okay, if this charge were, say, a negative charge, my little positive test charge would do something else. Right? It would follow a path toward. It would go toward, like this. So the electric field, you can imagine, is like pulling toward this negative charge. Whereas this is repelling away. Okay? Questions so far? I know this is really abstract.
So the test charge is always positive no matter what the...
No matter what, the test charge is always positive. Okay? That's how we know that if you pick up some sort of academic paper from the other side of the world and they have electric field lines drawn in, you know that they are a positive test charge. Okay? It's the convention that we use. So, what is the electric field? It's a hard thing to imagine. It's easy to imagine a gravitational field because a gravitational field is the acceleration due to gravity at any point at some distance away from an object. So you know what acceleration is, right? So if I say the gravitational field is the acceleration, then you're like, oh, it's just the acceleration. With electric field, it's a little bit weirder of a thing to think about. The electric field has units of newtons per coulomb. And what that means is, if I have a 1 coulomb test charge, how many newtons will be exerted on that if I place it in the field? And how many newtons per coulomb can the field create, or will the field create, when another charge is interacting? Okay, so it's this weird thing where you have the field, right? Everything has an electric field around it, every charge, but it doesn't do anything until it interacts. So it's basically like predicting how the interaction will go. So the units are newtons per coulomb, which is a force divided by a charge. Okay? The force is the Coulomb force. It is the electric force that we have been talking about so far. I find it helpful to imagine that the charge in question is like really important and that the test charge is not very important. And so I like to write my Coulomb's law with a capital Q for the important one and then like little q for the test charge. Like this is the test charge and then this is the important one, the one that we're talking about, the charge in question. Okay, that would be like with the Earth, it would be like big M is the mass of the Earth and little m is like you as you fall towards the Earth. Okay, the one that matters in the problem is the Earth. We're talking about the field of the Earth. So if it's a force divided by a charge, it is F over some charge. And the charge is the test charge, the imaginary charge. Okay? And so if you are talking about an actual charge, then I think I'm saying imaginary too much. The test charge doesn't have to be imaginary. Okay? It can be a real thing that you actually put in the field and see what happens. Okay? But it still is a test charge because it's put there to see what happens. And this equals the electric field, which is a vector. Okay? So the value of the electric field is the force experienced by a test charge divided by that test charge. Because the test charge doesn't matter. It's not really part of it. Okay? Another way to imagine that, or another way to quantify what the electric field is, without needing or requiring the presence of a test charge at all, is to say, okay, well, it's the force divided by the test charge. So the equation for the electric field from a single charge is K times the charge divided by the distance from that charge squared.
Okay, so you with the arrow over to the
Electric field vector. Now, what you'll notice here is that this is not just some constant value, right? If I have some positive charge, the electric field here, close, is different than the electric field here. In the same way that the electric force drops off as 1 over r squared, so does the electric field. So the space around a charge that it is influencing, the influence decreases as you get farther and farther away. Okay, just like a gravitational influence would get smaller as you get farther and farther away. So it's not some constant value. Okay, if I were to draw a vector that represents the electric field, let's say this is some distance d away, and I drew the vector like this long. And then I doubled that distance, the vector would become a quarter of its original length. And if I doubled that again, it would become a quarter. It's a new classroom, I can't draw on the walls. I used to, that was okay. It would become like really, really tiny, like that. Okay? So you can see that the value, the vector itself, the length of a vector, represents how big the field is. And the direction represents, represents the direction of the field at that point. Okay, and so this is some unquantified number, but this is a quarter of that, and this is a ninth of that. Okay, and so it drops off by a lot. The value is not constant. Yeah, because this is, like if this is D, this is 2D, and this is 3D. I didn't have space, I was going to go 4D, but then. So it's not constant. Okay. How do you feel so far? Well, if you're not like screaming and running for the door, I think I'm going to call that a win so far. A really good way to visualize electric field is by drawing what we call electric field lines. Electric field lines are a representation of the true path that the test charge would follow from start to finish if released in that field. So for example, if I have a negative charge and I want to draw the electric field around the negative charge, first of all, we know the field reaches to infinity. However, we cannot draw all of it, right? So we have to start somewhere. So if I place a positive test charge right here, what path, exact path, will that positive test charge follow?
Straight where it is.
It will go straight to the negative. What if I put it here?
Straight there.
Straight to the negative. What if I put it here?
Straight.
Same towards, right? Now, the number of lines that I'm drawing is completely arbitrary. I'm just going to draw them until I get bored. But notice that they are fairly evenly distributed. Okay? They should be evenly distributed, and they should be in the, what we call radial direction, right? Radial means either going straight in or straight out. Okay, so these ones are going straight in. And this is a way to visualize what would happen to a charge in this field. Everything that's released in this field, every positive charge that's released in this field is going to go straight towards the negative. Okay, so this is what we would call, what we would represent the positive charge as. Sorry, a negative. A positive charge, if I place a positive test charge right here, what will it do? Go straight away, straight away, straight away, in the radially outward direction, like so. Now you might wonder why it's necessary for us to do this. Obviously, you put a positive test charge anywhere near a positive charge and it's going to go away, straight away. You put one anywhere near a negative test charge and or positive test charge near a negative charge is going to go straight towards it, no matter what. But the electric field lines become more interesting when you talk about the electric field of a system of charges. For example, if I have two charges that are sitting here like so, fixed, and I ask, okay, if I put a positive test charge somewhere in this field, what will it do?
Depends on how
Go
far
towards
it is from each charge.
Absolutely, because it's experiencing not one electric field, but two. Right? It's experiencing one from the negative and one from the positive. So if I were to place one, let's put one right here, what would it do? It would go straight left, right? What if I put one right here?
So right.
Right.
Okay. What if I put one right here?
Oh, right to the right.
Okay. What if I put it right here?
Perpendicular to negative. Or
Diagonal?
No, I'm asking you. You said down.
Diagonal.
No.
So what?
Yeah.
I think it would not be a straight line. I think it'd be like a.
Yeah.
It would be a. Mischief, wouldn't it be like a curve? Because it's
an exponential line.
like that, and like once it escapes,
So initially, since it's closer to the positive, it's going to repeat. It's going to it's going to experience more of a repulsive force. But then, as it gets closer to the negative, it's going to be attracted to the negative line. So do something like this. This one will go out and then come back in, out.
Taylor, what does this remind you of? No.
I was just going to ask the same question. What does this remind you of?
Magnets, magnetic
Yeah.
fields.
I think I had in our calculator and go from chapter.
Really?
Something like this shows up.
It looks like
Plans.
what it looks like magnets, right? What either if you've ever looked at, I don't know why you would have it unless maybe I showed you the magnetic field of the Earth, right? This is what it looks like. Tilt your head to the side.
What is in your house?
North Pole, South Pole, right? Magnetic fields are almost exactly the same situation as electric fields. Okay. Have you ever taken a magnet and then put the iron filings on top?
Yeah.
Right? This is it. This is what it does. Okay, same exact thing. The iron filings, if you take a bar magnet, north-south, they align themselves like this,
Oh, I see.
like that. Okay, it's the same idea.
Wait, so does that mean that there's less of a pull on the polar ends of it? Because there's a... I'm confused right now.
We would have to do a calculation to find out that answer, but yes, I think so. Yep. Okay, so what if I have instead two positive charges that are next to each other?
It's going to be pushed away.
If I put a positive test charge here, what will it do? Okay? And what about here? Okay? What about here?
Just back down.
It's stuck in
It would go towards the other one, like straight, and then it would kind of loop
Just
down
get
or
stuck
up.
in.
Yep. It'll either go up or down. Same thing on this side, it's symmetric.
What, if
Does it
it's
just
straight
matter
in the
which
middle,
ones
does it just go?
it's like torn, if it's torn up a little more?
Yeah.
Close up.
This will do that, but slightly
What if
less.
they did it like perfectly in the middle? What?
I don't know. Something like this.
You know what?
I do not know what happened.
If you put it in
Wait,
the
you mean
center,
perfectly in the middle right here?
Yeah.
If you place a charge exactly
just
between the two, the net force will be 0, therefore it will not accelerate. So if you can place a charge perfectly at rest, then it will stay perfectly at rest.
Oh, that's tiny.
I want to show you briefly why physics is beautiful.
Wait,
So this is a simulation where you can place a charge and it will show you what the field looks like. Okay, notice that the density of lines represents a larger field. So closer to the charge, the lines are closer together. So it's a larger field value. Okay, farther away from the charge, they're getting farther apart, so it's a
Are
smaller.
there arrows on this?
And yeah, you can't really see them. I wonder if this one might be better, actually. Let me try this one. Nope, that one's worse. Okay. Yeah, so you can see the arrows are going away. It's hard to, it might be hard for you to see. If I place another charge, you can kind of see what happens. But then it gets cool. You can do another one, another one, another one, another one. And this is when it becomes important for you to be able to calculate the path that a test charge placed in this field would follow. Right? It becomes necessary for you to be able to do that. We can do the same thing with negative charges. You see it's going towards.
Wait, what about the one on the left side that says that it would have an arrow plot? So,
I didn't want to confuse you. This is sort of like what I was drawing before, but they're not getting smaller like they're supposed to.
it's like 3
You know how I was drawing them smaller and smaller and smaller? They're not doing that. So, but you can, it's a very similar thing, except it does individual vectors instead of doing. Okay. This is way too complicated? Yeah, especially to draw, right? If I ask you to draw this, it's not that bad. But then I say, instead of drawing one big line, draw a bunch of little vectors. Then it's like kind of annoying. So anyway, so over here, you can see that if I put like positives and negatives together, it becomes, I mean, this isn't like a physical thing that you can see, but look how cool that is. Right? You could arrange charges in such a way that you can influence the path of a test charge to do whatever you want, right? You can make a test charge do anything that you want. So you can make it like super complicated, and imagine the amount of computing that goes into some of these calculations, right? If you have too many charges. I think I overloaded this once and it was like, no, thank you, I can't do it anymore. But, oh, there we go. But you can kind of see like, it's just so cool. But there are rules that these lines follow. These are easy to draw, but they follow a set of rules that these are also following. Okay, and you need to know what those rules are, and I'm going to tell them to you right now.
put like 3 positive ones like right on top of it.
Okay. There are only 4 of them. The first one tells you which direction the lines go. And the way it's worded sounds a little bit strange to start with, but it will make total sense when I explain it. Lines begin on positive or infinity and end on negative or infinity. Don't freak out. When I say begin on infinity, if I have a negative charge here, I can't actually begin at infinity, right? But my line appears to come from infinity, right? It's like that line goes on forever to infinity. And it ended on the negative. Okay? If I have a positive charge, the line will start on positive and then end at infinity. The arrow is saying, I'm going to infinity. This arrow is saying, I came from infinity. Okay? That's what the infinity means. Don't think that you have to draw infinitely long lines or anything like that. So both of these follow that rule, right? Also, every single one of these follows that rule. But if I gave you this picture, imagine on a test, okay? I give you this picture,
Wait, the little arrow one?
the one on the right.
Will you ever do that many?
Hold on. I give you the picture without the signs. And I say, tell me what sign each one of those charges is.
Yeah, you can do that.
No problem,
Well, are
right?
the arrows there?
The arrow, yeah, the arrows are there.
Okay.
Yeah.
Then yeah.
Then if it's going towards it, it's negative. If the arrows are going away, then it's positive. Because they follow those rules without question. Okay, every single line will follow the rule that it goes towards negative and away from positive. So I could give you that. Honestly, I did that once actually on a test. And I just took out the minuses and the pluses and I said, tell me which ones are positive and negative. Everybody got it right.
You should do that.
I will. I'm telling you right now, it's going to be on your test. So, okay, the next rule is lines can never cross.
Why?
The reason is, what the line is representing is the electric field at that point. You can't have the net electric field at that point. You can have a bunch of electric fields at a given point, but you can't have a net electric field pointing in two different directions, right? An X that, if they crisscross like this, that's saying, well, sometimes it's pointing this, if you put a test charge, sometimes it'll go this way, and sometimes it'll go this way, and sometimes it'll go that way, and sometimes it'll go that way. Sometimes it experiences this electric field, and sometimes it experiences that electric field. If there are two electric fields here, you would end up with a net electric field that points in one specific direction. Okay, there's no way for them to cross. They can never cross. It's impossible. Sometimes in the simulations, because it's like overloaded, it'll cross. But they cannot cross.
But they'll conjoin something. They'll conjoin in the negative.
They should never join. They should never join.
But follow a similar path.
Okay.
Yeah.
The number of lines touching a charge is proportional to the charge. Here's what that means. These don't have arrows, unfortunately, but you can see what I've done is I've placed a small charge and a large charge. The number of lines touching the smaller charge, not smaller size, but like smaller charge, is a fewer number of lines because it's a smaller charge value. This one has a larger charge value, therefore there are more lines touching it. Okay? You could even quantify that. Let's say the smaller one had 4 lines touching it and the larger one had 8 lines touching it. You could say the larger one has twice the value of the smaller one. Okay? Does that make sense? So that's what proportional means. If I increase the number of lines proportionally, then the charge increases proportionally to that. Okay? Okay. And then the last rule is line density represents E field, electric field value. So higher density means larger value. Okay, when they're closer together, they have a larger value. So it's not going to be that I ask you to draw something like very complicated, right? It's more like you look at them and you analyze them. I can ask you things like, is it positive or negative? Which one has a bigger charge? Is it correctly drawn? What's wrong with it? That kind of thing. Okay, but it's not going to be like, here are 37 charges, draw the electric field, go. That will never ever happen, I promise. Okay, the most I'll ever ask you is 2. 2 positives, 2 negatives, or a positive and a negative.